Salam, peace be upon you. My name is Muhammad Layak Siddiqui, the father of holophase. We began with one insight. Pattern is primary. Phi is circular comparability, the root permission for distinction. Only relations are public. Identity is invariance under lawful transformation. Persistence is certified survival through change. Interaction is joint constraint. Time is ordered transformation. No ex nihilo. Every appearance has provenance. The observer is a pattern within pattern reality. Measurement produces traces. Memory stabilizes them. Models compress structure. Prediction narrows lawful futures. Learning updates structure while preserving identity. Intervention alters coupling. Computation transforms patterns under rules. Information is constraint on possibility. Publicness makes knowledge shareable. Now we ask, why do observers sometimes see different aspects of the same pattern? 1. The first intuition about scale. In everyday language, scale usually means size. We say something is large scale or a small scale. We zoom in or zoom out. We speak about microscopic and cosmic distances. But in Phi Pattern science, a scale means something more profound. A scale is not just how big something is. A scale is how we access a pattern. To understand this, imagine looking at the Earth from different distances. From space, continents appear as smooth shapes. From an airplane, mountains and rivers become visible. From the ground, rocks and trees appear. From a microscope, grains of soil reveal crystals and microbes. The Earth itself did not change between these views. What changed was the regime of access. Each scale reveals a different phase of the same pattern. Scale, therefore, determines which aspects of a pattern become visible, stable, or invisible. A simple, everyday example: the photograph of a face. Think of a photograph of a human face. If we zoom in very close, so close that we see only a single pore, we see texture, maybe a tiny hair, maybe a speck of dust. We do not see the nose, the eye, the expression. If we zoom out to see the whole face, we see the shape, the features, the expression. We lose the pore details. If we zoom out further to see a crowd, the face becomes just one dot among many. We lose individual features entirely. Which view is correct? All are correct. Each reveals something real about the face, but at different scales. The face is one pattern. Scale determines what part of it becomes visible. Scale as an access regime. To understand scale clearly, we must stop thinking of it as merely zooming in or out. Scale is a structured access regime. An access regime includes several components. Window size. How large an area we observe. A small window shows local detail. A large window shows global structure. Resolution. How finely we can distinguish details. High resolution reveals fine structure. Low resolution averages over it. Sampling density. How many measurements we take within a region. Sparse sampling may miss rapid variation. Dense sampling captures it. Derivative ceiling. How deep our analysis of structural change can go. Some windows support only value, others support rate of change, curvature, and beyond. Observational duration. How long we observe the system. Brief observations show snapshots. Long observations reveal dynamics, cycles, evolution. Coarse graining level. How much detail we intentionally smooth or average. Different groupings reveal different patterns. Together, these elements determine what part of a pattern becomes legible. If any of them change, The visible structure may change. The pattern remains the same, but our access to it changes. The river example. Imagine standing beside the river. At first glance, the river seems smooth and flowing. At this scale, the river appears as a continuous current. Now move closer and look carefully. You begin to see swirling eddies. Move closer still, and you notice small ripples around rocks. Examine a droplet under magnification, and you see molecular motion. At each step, the river looks different, yet it is still the same river. The difference lies in the scale of observation. At coarse scale, we see flow. At finer scale, we see turbulence. At molecular scale, we see random motion. All these descriptions are true. They are simply different scale readings of the same pattern. Another example, the coastline. A coastline seen from space is a smooth curve. From an airplane, it shows bays and peninsulas. From a boat, it reveals cliffs and beaches. From ground level, it shows rocks and sand. Under a microscope, it shows grains of sand, each with its own shape. Which is the real coastline? All are real. The coastline exists at all these scales simultaneously. Our access regime selects which aspects we see. This is why the length of a coastline depends on the ruler we use, a famous discovery in mathematics. Smaller rulers reveal more detail, longer coastline. There is no single true length. Length is scale dependent. Same pattern, different appearances. One of the most important lessons of scale is this. The same pattern may appear radically different at different scales. At fine scales, we may see fluctuation, noise, individual events. At coarse scales, we may see order, regularity, smooth trends. At intermediate scales, we may see transitions, boundaries, critical points. At critical scales, we may see phase changes, bifurcations, emergent structure. All are real. All are the pattern read through different access regimes. Consider sand on a beach. From far away, the beach looks smooth. From a few meters away, we see ripples shaped by wind. Up close, we see individual grains. Under magnification, we see crystals with complex geometry. Each description is valid. None is the entire story. They are scale-dependent views. The beach pattern contains all these structures simultaneously. Scale simply determines which structures become legible. 7. Fluctuation and order. Scale also explains a surprising phenomenon. At very fine scales, systems often appear chaotic. At larger scales, they become orderly. Consider air molecules in a room. At microscopic scale, each molecule moves unpredictably. But at human scale, we experience stable temperature and pressure. The underlying randomness averages out. Order emerges from fluctuation. This does not mean the fluctuations disappear. They simply become invisible at that scale. Thus, scale determines whether we see noise or stability. 8. Intermediate scales and transitions. Between fine and coarse scales lies an intermediate region. This is where patterns change character. Water molecules illustrate this beautifully. At molecular scale, we see individual molecules moving randomly. At a slightly larger scale, we observe droplets forming. At a still larger scale, we observe waves. The transitions between these regimes are not sudden jumps. They are smooth transformations in the legibility of structure. Scale, therefore, governs pattern transitions. Critical scales. Some patterns reveal dramatic changes at certain scales. These are sometimes called critical scales. Consider ice melting into water. At molecular scale, the difference between solid and liquid emerges when temperature crosses a threshold. Similarly, in social systems, a small number of interactions may appear random, but large populations can produce stable trends. Critical scales mark points where new forms of organization become visible. The pattern was always present in potential. The correct scale simply reveals it. Scale invariance. Although patterns appear different across scales, some properties remain stable. These stable features are called scale invariants. For example, the shape of a coastline often looks similar whether viewed from a satellite or from an airplane. The exact details differ, but the overall structure persists. Similarly, the laws governing planetary motion remain valid across many scales. Scale invariants reveal the deep structure of patterns. They show what aspects of a system remain stable despite changes in observation regime. In Phi pattern science, these invariants are extremely important. They indicate which features belong to the underlying pattern rather than to a particular scale. A forest across scales. A forest provides another powerful illustration. From space, we see a green region. From an airplane, we see clusters of trees. Walking through the forest, we see individual trunks and branches. Examining a leaf reveals veins and cells. Studying a cell reveals molecules. At each scale, the forest appears differently organized. Yet, the forest pattern contains all these levels simultaneously. The scale regime determines which structures dominate the description. Scale mismatch and false disagreement. Here is one of the most important practical applications of scale understanding. Scale mismatch can create false disagreement among observers. One observer sees fine structure, another sees coarse structure. They may argue about what is really there, but both are right. They are seeing different aspects of the same pattern. Many scientific disagreements are scale disagreements in disguise. A biologist studying individual cells might argue with an ecologist studying whole ecosystems. Both are studying the same organism, but at different scales. Their findings are not contradictory, they are complementary. A physicist studying quantum fluctuations might argue with a cosmologist studying galaxy clusters. Both are studying the same universe, but at vastly different scales. Their theories are not incompatible, they are scale specific. When disagreement arises, we must first ask, are we operating at the same scale? If not, the disagreement may be illusory. The city example. Imagine two researchers studying a city. One analyzes satellite images. The other studies pedestrian movement on sidewalks. The satellite researcher sees traffic networks and urban layout. The pedestrian researcher sees crowd behavior and individual choices. Each describes a different pattern, but both patterns belong to the same city. The difference lies in scale. Without recognizing scale regimes, they might believe they disagree. With scale awareness, they realize they are examining different aspects of the same system. The economy example. An economist studying individual consumer choices might conclude that people are irrational, inconsistent, swayed by emotion. Another economist studying aggregate market behavior might conclude that markets are efficient, rational, self-correcting. Who is right? Both may be. Individual behavior is messy, aggregate behavior can be smooth. The scale of observation changes what patterns are visible. The apparent contradiction dissolves when we recognize scale dependence. Scale and emergence. Now we can preview a deeper concept that will be developed fully in Part 44. Many patterns emerge only at certain scales. The pattern was always there in potential, but scale transition makes it legible. A hurricane emerges from atmospheric conditions at large scales. You cannot see a hurricane by studying individual air molecules. The pattern appears only when you zoom out. Consciousness emerges from neural activity at large scales. You cannot see thought by studying individual neurons. The pattern appears only when you observe the whole brain. Life emerges from chemical processes at large scales. You cannot see life by studying individual molecules. The pattern appears only when you observe organized systems. Scale is not emergence itself, but the condition under which emergence becomes visible. The sand pile example. A sand pile looks stable from far away. Close up, grains are constantly shifting, falling, rearranging. At a critical scale, just before an avalanche, new patterns appear: correlations, precursors, scaling laws. The avalanche itself is an emergent phenomenon. It is not visible in individual grains. It appears only at the scale of the whole pile. Scale determines what we can see. The human body across scales. Consider the human body. At the scale of atoms, we see carbon, hydrogen, oxygen, nitrogen, elements interacting. At the scale of molecules, we see DNA, proteins, lipids, complex structures. At the scale of cells, we see organelles, membranes, nuclei, living units. At the scale of tissues, we see muscle, nerve, bone, organized systems. At the scale of organs, we see heart, lung, brain, functional modules. At the scale of the whole body, we see a person, moving, thinking, feeling. At the scale of society, we see roles, relationships, cultures, collective patterns. All are real. All are the human. No single scale reveals the whole. Scale does not create hierarchies of reality. A common misunderstanding is to treat certain scales as more real than others. Some people say that microscopic physics is the only true description of reality. Others argue that macroscopic laws are the most meaningful. Phi Pattern science rejects this hierarchy. No scale is inherently privileged. Each scale reveals certain invariants and hides others. The goal is not to choose one scale as the ultimate truth. The goal is to understand how patterns appear across scales. Because no single scale reveals the entire pattern, complete understanding requires multi-scale observation. Scientists often move between scales. Astronomers examine galaxies through telescopes and also analyze simulations. Biologists study molecules, cells, and ecosystems. Economists analyze individual transactions and global markets. Each scale adds a piece to the puzzle. Understanding emerges from connecting these pieces. The scale principle. Now we can state the central principle of this part. Scale determines what part of a phi pattern becomes publicly readable. Different scales reveal different aspects of the same pattern. Some features persist across scales. Others exist only at particular scales. A pattern cannot be fully understood from a single scale alone. Multi-scale observation is necessary for deep comprehension. 21. The rigor layer, the scale gate. Because scale matters so much, pattern claims must declare their scale regime. This requirement forms the scale gate. The scale gate asks, what is the observational window size? What resolution is used? What sampling density is applied? What derivative depth is available? What duration of observation is involved? What coarse graining level is applied? Without these declarations, pattern claims become ambiguous. Observers may unknowingly compare different scales. The scale gate requires Scale parameters, all relevant dimensions declared. Scale dependence, acknowledgement that what is seen depends on scale. Scale invariance, what persists across scales if claimed. Scale limitations, what cannot be seen at this scale. Scale mismatch resolution, how apparent contradictions with other scales are resolved. 22. Additional gates. Several related gates reinforce this discipline. The read depth gate ensures that claims do not exceed the structural detail supported by the data. The aliasing gate checks whether sampling is sufficient to avoid misleading patterns caused by undersampling. The cross-scale comparability gate ensures that results from different scales can be meaningfully related. The scale inviolability gate verifies claims about properties that persist across scales. Together, these gates protect pattern science from confusion caused by hidden scale assumptions. Firewalls against scale confusion. Several firewalls prevent misuse of scale concepts. Firewall 1. No treating one scale as the ultimate reality. No single scale reveals the whole pattern. Do not treat your scale as the real one. Firewall 2. No ignoring scale dependence when interpreting data. What you see depends on your scale regime. Declare it. No conflating scale with reality level. Different scales show different aspects, not different levels of reality. All are real. No disguising scale mismatch as scientific contradiction. When observers disagree, check scales first. The disagreement may be illusory. No treating scale artifacts as pattern features. Some features appear only at certain scales because of the access regime, not because they are intrinsic. No assuming infinite resolution. Resolution limits are part of scale. Declare them. No ignoring coarse graining choices. How you group fine details shapes what you see. Declare it. These protections maintain clarity in pattern interpretation. Refusal conditions. We refuse to certify a scale-dependent claim if scale parameters are not declared, scale dependence is ignored, scale invariants are claimed without demonstration, scale mismatch is hidden when relevant. One scale is treated as exhaustive. Resolution limits are assumed infinite. Coarse graining choices are undeclared. Refusal here is not pedantry, it is protecting the richness of multi-scale reality. Why this matters beyond science. Scale in life. Scale is not only for science, it is for how we understand everything. In relationships, we see people at different scales. A single interaction shows one face. A year of shared life shows another. A lifetime reveals yet another. Which is the real person? All are real. Scale determines what we see. Disagreements in relationships often arise from scale mismatch. One person focuses on a single hurtful comment, fine scale. The other focuses on years of care, coarse scale. Both are right, but they are seeing at different scales. Understanding scale helps us recognize that apparent contradictions may be complementary views of the same pattern. In politics, we see events at different scales. A single news report shows one angle. Historical analysis shows another. Both are needed. In self-understanding, we experience ourselves at different scales. A moment of frustration shows one aspect. A decade of growth shows another. Both are real. Scale teaches us humility. No single view captures everything. We need multiple scales to approach the whole. A final image, the mountain and the climber. Imagine a mountain climber ascending a peak. From base camp, the mountain looks majestic, whole, a single form. Halfway up, the climber sees cliffs, ridges, snowfields, details invisible from below. At the summit, the view expands to horizons, other peaks, the curve of the earth. Which view is true? All are true. The mountain is one pattern. The climber's scale determines what is visible. The climber who insists that only the summit view is real misses the details of the climb. The climber who insists that only the close-up rocks are real misses the grandeur of the whole. To know the mountain, we must climb at all scales. Closing insight. We began with comparability. From phi emerged distinction. From distinction emerged pattern. From pattern emerge identity, persistence, interaction, measurement, memory, modeling, prediction, learning, intervention, computation, information, publicness. And now, scale. Scale is not a new ingredient. It is the access regime that determines what part of a pattern becomes visible. It is why the same pattern shows different faces at different magnifications. It is why observers can both be right while seeming to disagree. Scale teaches us that no single view is exhaustive. To know a pattern deeply, we must approach it through multiple scales. We now move forward. With scale understood, we can ask, how do we move between scales lawfully? That requires coarse graining, the declared loss of detail that enables scale transition. That is part 43. Always, peace be upon you.